Very sorry that I couldn't be there. I wish I could, but my doctor told me to stay home. Structs work because I think they're very specific to Swift and they work very different from what we expect in Objective-C. So let's start with a sample project and we'll start building more and more things and see how we can wrap Swift objects inside structs. So we're going to create a command line tool and we'll call it Swift structs, and if we open up main.swift, then we can run this program just to make sure that it works. So we get our hello world. I'll make this a little bit bigger, and everything works. So far, so good. If we create an array in Swift with 1, 3, 2 in there, then what we can do is we can sort the array and print this. So far so good. We can print and it prints 1, 2, 3. Exactly what we expected. But the thing to see here is that the sorting is not changing the original array. It creates a new array and sorts that. So it makes a copy of the original array and sorts it. If we print the original array below, we can see that it's unchanged. And if we try, instead of sorting a copy, and try to do array.sortInPlace, which mutates the array, it's not going to work. If we run this, we get an error. So what happens here? It says, can I use mutating member? And the sortInPlace is mutating. And the thing is, if you define a struct using let, you can never ever change it again. This is the expected way it works in Swift. So what the compiler proposes is to change it to a var. And now we can call sortInPlace and print it and run it. So only when we define a struct using var we can change it. With let, there is no way to change it. So this seems a little bit magical. And what we're going to do is we're going to create our own structs to see how we can sort of get this behavior and how this works under the hood. So let's create a person struct, and we're going to have a name in there, which is a string, and a var, age, which is going to be an integer. So we define the name using let and the age using var. So if we create a sample person, Lady Gaga, for example, Lady Gaga, who's 29 years old, we can print it. So build succeeded, and so far so good. This is very simple. Now, if you remember what we said before, which is you can never change a struct that's defined using let. Well, if we try to say h++, the compiler will give us a warning. And it says, hey, this doesn't work on let, make it a var. So if we follow what the compiler does, then we have a var. And this is essential to how structs work. So the moment you have a let, which is a struct, you can never change it again. Okay, let's go back and make sure that we cannot change the name to Taylor, for example. We define name using let, so there is no way this will ever work. So name is immutable forever. Cool. So this is how we can work with structs. So now let's change it back to a let and make a copy. Real Gaga. And we can change the age of the copy. And now we can print real Gaga with the new age, and we can print Gaga. So if we print this, we will see that the copy has an age of 30, but the original array is not changed. So what's happening here is when you create a new variable with a struct in it, it's always by copy. Structs are always passed by copy. When you create a new variable, when you call a function, you always get a copy. So structs are not shared by default. And what happened here is the real Gaga is a copy of Gaga, and therefore the original value didn't change. So this can be very useful behavior, because you know that if you define Gaga using let, it can never change. So nowhere else in the program can anybody change this. Okay, and this also works for functions. So let's have a look at how to create a function. So this is celebrate birthday. And inside the celebrate birthday function, we're going to pass a person. And then we're going to say person.age++. And then we're going to print happy birthday, now age years old. So this will not compile. So first of all, this needs to be person.age, and there's another problem. So here, Swift says, well, I cannot change a person. And what's happening here is every parameter is automatically defined using let. So really this is the same as writing the let. And that's why you cannot change the person. So I'll remove it again. What the Swift compiler tells us is, hey, please change this to a var. And now what happens is inside this function, the person is a variable. Still, the person is passed by copy. So changing the person inside the function does not change the original value. So we can check this. Let's remove this whole real Gaga stuff. And we do celebrate birthday, Gaga. Now, we can see that inside the function, she will be 30 years old, but the original value hasn't changed. Writing a free function is not really the nicest thing, because now in Swift we can write extensions. So let's write this function as an extension. Extension person, and close, indent it a little bit. If we write it as an extension, we do not need to pass in a person in anymore. So we can delete this part, and instead of person, we just write self.age. Now we get an error, and this is the same error as we had before, because what happened is we had this person, right? And if you define a struct using let, you cannot mutate it. So how can we mutate inside the celebrate birthday function? This should be illegal, and it is. So what the Swift compiler says, well, you can change the age if you want to, but then you need to mark the method as mutating. So let's do that. And now it's a clear sign that if we call celebrate birthday, we can only call it on a variable. So let's change it below Gaga.celebrate birthday. This doesn't work. So Gaga is defined using let. So we need to follow the advice and change it to a var, and then print it. So now it works. It says happy birthday, 30 years old. And it changed the original value. So that's really cool. And that's how structs work. And this mutating keyword is essential. If you forget it, the compiler will not let you build it. And this is also how arrays work internally. So it's not magic that you can call certain methods on a let and certain methods on a var. It's because they're defined as mutating. Cool. So let's remove all of this stuff and start working with NSData. So NSData is a collection of bytes, basically. It's a simple object, and it stores bytes. And there are two variants of NSData. There's NSData and NSMutable data. And the normal NSData you cannot mutate, so it's an immutable value. But the NSMutable data you can mutate. And this is a bit of a problem because the NSMutable data is a subclass. So let's consider a simple example. We create some sample data, which is an NSData, and we can just take a string and say data using encoding, NSUTF-8 string encoding, and we can print it. So this works, we get some bytes. Now what we can do is we can create a data variable, which is an NSMutable data, and then we can say data.append bytes. or append data. And now we can print it. So this works, and this will print the same bytes. But what's a really big problem is, if, let's say we create a function process data, which takes some NS data, and it checks if the data is non-empty. Otherwise it returns, because this function will process some data, and it will only work correctly if the data is non-empty, otherwise it crashes. So the problem is that we can call this function process data with our data, which is mutable. And because it's mutable, it means that it can be changed at any time on any different thread. So if we pass this data, mutable data, to a different thread, it might change just after the guard condition. So this is actually very dangerous. And Objective-C programmers know what to do. They need to make sure that there's always a private copy of the data inside the function. So what you would do as an Objective-C programmer is say something like input NS data, and then we say data equals input dot mutable copy as NS mutable data. And now you know that inside our function we are the only one who references the data. So now we know that nobody can change it under our nose. And the same problems exist with NS array and NS mutable array, and with NS string and NS mutable string. So this is a very common thing in Objective-C, and that's why we also have, for example, in Objective-C, we have this thing like property definitions, which are copy by default, because it's always safer to copy than to have this implicit sharing going on. So that's the cool thing about structs. In structs, we don't have this copying, we get this copying for free. We don't have to worry about it ourselves. So let's try to wrap an NS data into a struct and see what happens. So we create a struct data, and it has a private variable, which is an NS mutable data, and we start with just empty NS mutable data. And then we add an initializer, the data, which takes some NS data and appends it. Now we can also provide a default value, the empty data, and now we can create some variables. So we can say print data, and now we get an empty struct. Let's re-add our sample data. So what we can also do is we can initialize it with sample data, and this also works. Build succeeded, and now it prints the NS data. Let's make it a little bit more complicated, and let's add an accessor for the bytes. So as we said before, the NS data stores some bytes, and what we want to do is create a variable that gives us these bytes as an array. So bytes is a uint8 array, and in order to do this, we can call data.getBytes. And this takes an unsafe mutable pointer to void and a length. So the length is easy, that's just data.length. And this buffer needs to be some kind of C pointer. And if we read the documentation, it needs to be pointed to an array of uint8s. Luckily, this is very easy to do in Swift. So what it needs is some kind of result array, which is a uint8 array. And this result array has a count, and that's the data.length, and we just fill it with zeros. So it already has the right size. And now we can use &result and pass it by reference to the getBytes functions and then return it. So this seems to work. Let's print data.bytes. And we get the bytes as an array. And note how this is much nicer, much more Swift-like. So instead of having to call this getBytes method, and do all the complicated stuff with pointers. We just wrapped it and made a really nice Swift API, and we can just say data.bytes. So that's really cool. What about mutation? And this is where it gets more complicated. So if we create a copy, then what we want to do is we want to add some kind of function that allows us to say copy and then maybe append some data. So let's write this append function. So we're going to write a function append which takes some NS data, and it just says data.append data other. So now we can, for example, say here data.append and append the sample data. So now hopefully this will still print the same bytes. So that's cool, but there's already one problem. We defined our data using let, and yet the compiler allows us to call append. So we really need to change this. We need to change it to var, and we want the compiler to enforce this. So the reason is the reason why it allows us to call append is because there is no mutating keyword, and we need to write mutating. And the compiler doesn't force us to write mutating because we're not changing the struct. We're changing, because the struct, what it does, this data is a pointer to an object, and we're not changing the pointer, which is stored in the struct. We're changing the object, but the Swift compiler doesn't know about this. The pointer stays the same, and that's why. So we can say data.append, and now we get the error that we wanted, and we need to change it to a var. And only when we have a var we can append. So far so good. Let's do this copy thing. So if we say copy equals data, what we really want is that copy is now empty. And if we print data.bytes and then print copy.bytes, we expect the bytes for hello, and then we expect an empty array. But this doesn't happen. So instead of the empty array, now we have two arrays that are the same. So what happened here? The problem is that the structs, again, when we copied, it copied the pointer, but it didn't copy the object. So both structs have a different pointer to the same object. So when we change the one struct, the other one changes also. That's not really cool. And what we need to do is to change this append function. So what we need to do here is to say data equals data.mutable copy as mutable data. And this makes a copy of the object before we change it. And now you can also see that Swift doesn't, we need to write mutating here. So Swift doesn't allow us to write this without mutating. So let's see what happens. Now we get 5 bytes and then an empty array. So now we have finally a semantically correct data struct. Except there's still one problem. And this is slightly more advanced. So the problem is that this is very inefficient. Anytime we make a small change, a copy is made, even when the data is not shared with anybody else. So for example, if we put this append in a for loop and loop over it 5 times, then there will be 5 copies made. And really, we only need to make the copy the first time, because we share it between data and copy, but after that, we don't need to make any copies anymore. And the way we can solve this is using isUniquely reference. So we can say isUniquely referenced non-Objective-C, and then pass in the data. And this check will only succeed if there's a unique reference to the data object. So if nobody else is sharing a reference to this data object. And if there is a reference shared, then we need to make a copy. If there's no reference, we only need to append because nobody else is sharing this anyway. So let's try to run this. And the other thing I want to do is, in case we do make a copy, I just want to print making a copy. And hopefully we see this only once. Oh no, there is 5 times making a copy. So what's happening here? Well, if we look at the name of the function, it's called isUniquelyReference non-Objective-C. And the reason why it's called like this is because it only works in Swift objects. It does not work on Objective-C objects. So we need to find some way to create this NS, to take this NS mutable data and make it into a Swift object. Unfortunately, there is not a very simple way, but I will show you the easiest way we can do this, and that's using a box. So we can create a new class box, which takes a single parameter, the type. In our case, it will be NS data, and it stores this parameter. And then, oh, I'm sorry. And then there's an initializer, which just stores the parameter. So now what this allows us is to take any kind of type and put it into the box and make it into a Swift object. So we can create a box with structs, with Objective-C objects, anything we want, and the result will be a Swift object. So we need to change the type of this data variable, and also here we need to box it up. And now everything will break. But luckily it's easy to solve this. So we say data.unbox, 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 and also here and here. And there's one more small change we need to make, and that's when we create the copy, we need to box it up again. And hopefully now our program still compiles. Yes. So now the copy is made only once, and we still have the struct semantics. So we never have to worry about copying again. We solved this problem inside our implementation, and any user of the struct gets it for free. And I think this is a super powerful technique because there's all these classes that exist already and that are really well done. For example, all of Cocoa is super useful, like things like NSData or NSString. And if we want to, we can make our own wrappers around it. We can make our own structs that use these existing objects and existing frameworks to get struct semantics. And this technique using the isUniquelyReference may look a little bit complicated, but once you get the hang of it, it's the same almost everywhere. And it's a very powerful technique to know. So that's really all I have to say. I hope you have questions, and I'm happy to take any. If you prefer to, you can ask the question in Russian, and I'm sure that we can get somebody to translate it. Thank you.
Нет, мы же не облегчим Крису задачу. Крис уже в скайпе, он нас слышит. Какие-нибудь вопросы, потому что мы услышали сейчас?
Skype, any questions about presentation that has just been delivered to us? Looking for raised hands. So this is the most modest report in terms of asking questions. So I see a person with a raised hand over here.
As I understood, this realization of the structure wouldn't be thread safe because of time between call to function that that function that asks is there is unequal pointer and time where copy called, or it's don't make sense.
I'm not sure. I haven't thought about it. I think the isUniquelyReference, in worst case, it will return false, so saying it's not unique. But you might be right. I haven't thought about that. We would need to write a test case, I think. But I think worst case, it will make an extra copy. But yeah, I'm not completely sure.
Any other questions?
I can hear you, but I cannot see you. But you can see me, right?
Hey Chris, Dan here. So it sounds like the bigger issue we're talking about here is that the entire of Cocoa is written in Objective-C, and now we have to go through all these hoops to make it safe again. So would you recommend that we do this, or should we wait for Apple to migrate its code base to Swift?
Yeah, that's a very good question, and I'm not sure what the best answer is. So I'm trying to use structs everywhere where it makes sense. If I need to use objects, I'm happy to use objects. I don't think the goal is to use structs everywhere. And it's easiest to use them if they are composed out of other structs, like strings and ints and stuff like that. But if you want to use something like NSData, you basically have to use either Apple's NSData or you have to write your own version. And it depends a bit. I think there is something to be said for just using NSData because it's very well tested. The Apple engineers have put years of effort into this. Yeah, but if you use this a lot throughout your code and safety is important for you, or speed, then it might be interesting to wrap it in a struct. It's not very hard. And the third option would just be to write your own version, but then I think the chances for bugs are much higher than when you use Apple's code. So I think it really depends on your application. If you use some kind of data structure a lot or some classes, you can either use them as is, or you can write a completely brand new version without any dependency on the old code, or maybe you could use this technique of the is uniquely referenced to create a simple wrapper around it. And yeah, I think there is no right answer for all cases, but I think it really depends on your specific problem.
Okay, thank you. Next question, please.
Hey, Chris, thanks for the talk. A small question about the code reusability. From your experience, this approach with boxing, unboxing, and transforming to structs and stuff, is it reusable? Is it possible to create a framework on this basis and reuse it in different projects, or it's really project tied, like with if you have Lady Gagas or then you have dogs and stuff like that? Like, what's about code reusability?
Yeah, I think it's not any different from any other kind of approach. So the thing, like, for example, the box class, you could definitely reuse that everywhere. It's useful in some other places as well. And the nice thing about this writing, for example, a struct wrapper, is that it is very reusable. So this data wrapper, I think somebody could take this code and make it into an open source project, and then everybody can reuse this. And one of the nice things about structs is it's very hard to do something with global state and singletons, for example. So I would say even by default, structs are a little bit more reusable. And yeah, I don't know if it changes a lot, but it might help a little bit. Yeah.
Okay, thanks.
Chris, thank you much. Thank you very much.
Thank you.
It was Chris from OptCIO. You are in our heart.